right, cool. We are doing AP review. This is 2014 BC Free Response 5. We're looking at a region R that is bounded by y equals x e to the x squared, y equals negative 2x, and x equals 1, right? So first part, we're asked to find the area of R. So when we're asked to find an area, all of these curves intersect at 0, and this is the end boundary of 1. So we're going to do top curve minus bottom curve, right? So for part A, the area is going to be the integral from 0 to 1 of the top curve, which is the x e to the x squared, minus the bottom curve, which is a negative 2x. If you want to make it a minus a negative 2x or a plus 2x, I don't care. Either one's fine. And then I'm going to integrate both of those. So technically, this is u sub, right? If you need the u sub, like if you need to write it out, your u would be x squared, your du would be a 2x dx, meaning that you're going to end up with a 1/2 in front of this thing, essentially. Like you're going to end up with a 1/2 in front of the e to the u du, right? So there's going to be a 1/2 e to the u du if you need it. If you don't need that, if you're able to just in your head realize that you're going to have to divide by 2, that's also awesome. So I'm going to get this a 1/2 e to the stuff, right? Plus this x squared from 0 to 1. When I plug that in, that's going to be a 1/2 of an e plus a 1, right? And then minus, and be careful because when you're plugging in zeros to exponentials, they're not going to disappear. 1/2 of an e to the 0 plus 0. So I end up getting that this is a 1/2 e plus 1 minus a 1/2. So I get 1/2 e plus 1/2. And if you want to factor the 1/2 out, you can. If you want to put everybody over 2, like you could, right? This is a 1/2 times the quantity e plus 1. You could write it as an e plus 1 all over 2. Any of those are also fine. It doesn't matter, but you just need to have a right answer. Cool. Part B. Write but do not evaluate an integral expression that gives the volume of the solid generated when that region R is rotated about the horizontal line y equals negative 2. Well, it's convenient that they pick something below this so that I could draw it down here and not run into the stuff at the top. So here's the line where y is negative 2, and you can see that because if you plugged in x is 1, which is this line, to this line, like this vertical line is x is 1, if you plugged x is 1 into this second equation, you'd get that at the moment when x is 1, the y value is negative 2. So you're rotating around this. What's going to happen is you're going to be taking this little miniature slice somewhere in the middle and rotating about this axis of rotation. So you're going to get what we call an annulus, right? It looks like essentially a washer, right? So sometimes you'll hear it called the washer method. So the area of a washer, right, is pi big R squared minus pi little r squared, meaning it's the area of the outside of the washer minus the area of the hole that's cut out of it, right? So if you want the volume, you just integrate all of the washers, right? You add all of those washers up. So my big R in this case is going to be the top curve, which is this kind of crazy thing, minus the negative 2. So the big radius in this problem is the top curve, x e to the x squared, minus a negative 2, so plus 2, right? Or minus a negative 2 if you want to leave it that way, it doesn't matter. My little radius is this bottom curve minus the axis of rotation. So that's going to be a negative 2x minus a negative 2, or plus 2. So what that means is the volume is going to be the integral from 0 to 1 of pi big R squared, and you can yank the pi out if you want. So pi big R squared, so see how up here if I wanted I could pull the pi out and make it big R squared minus little r squared. Just make sure you're still individually squaring the r's. It is not the quantity that is squared. So pi big R squared, big R was x e to the x squared plus 2, quantity squared, minus little r was negative 2x plus 2, also squared as a quantity with respect to x. And that's what they want. Right? That's what they want to see. They don't want you to evaluate it, which was nice of them because that would be no fun at all. Part C, write but do not evaluate an expression involving one or more integrals that gives the perimeter. Cool. So the perimeter of this thing is going to be the arc length, essentially, of each one of these curves, right? So in order to find the arc length, so the only one where you actually have to find the arc length is, I did a terrible job of drawing all over my graph. Hold on. The only one where you actually have to find the arc length is the curvy one, because the two that are lines you could actually figure out, right? So you could find this length, because this is a hypotenuse of a triangle, right, that has an x coordinate of 1 and a y coordinate that we've already established of negative 2, right? So you could find this hypotenuse really quickly as 1 squared plus a negative 2 squared inside a square root. This hypotenuse is a root 5. So you can find this length very easily. It's a root 5, right? By the same argument, you can also find the length of this line very easily, right? So I've got this piece easily without using arc length. I can find this piece pretty easily too. I already know this part of this piece is a 2, right? It's technically a -2 in terms of position, but it's a 2 in terms of the length, right? And then I can find this piece, right? I can find this piece because this piece is literally just the y value of y equals x e to the x squared at x equals 1, right? Because this is the line where x is 1. So y equals 1 e to the first. Oh, it's just an e. So this is e. So now I know this blue length is root 5. I know this length is an e plus a 2, right? So the only piece that I need to do the actual arc length formula for is this black chunk here, right? So I need the arc length formula for this. So the perimeter, right, the perimeter of this thing for part C is going to be the blue line, which is just part of a triangle because it is linear, right, plus the red line, which was an e plus 2, right, plus, and now I need the arc length of the other curve, right? So now it involves you actually remembering how to find the arc length of something, right? So a quick review of how arc length works, right? So arc length is the integral from, let's say, a to b, which in this case it will be 0 to 1, right, of the square root of 1 plus dy dx quantity squared with respect to x, right? So I need the derivative of this thing. So if y equals x e to the x squared, my y prime is u. dv is going to be e to the stuff times the derivative of the stuff plus v du is just a 1. So I'm going to get, and I could leave it like this, to be perfectly honest. It doesn't matter. I can leave it as this entire giant ugly monstrosity quantity squared. That's fine. So this piece is going to be the integral from 0 to 1 of the square root of 1 plus, and then this ugly thing, clean up if you want or don't if you don't, doesn't matter. I'm probably going to make this a 2x squared, e to the x squared, because it's a little bit nicer, plus e to the x squared. So 2x squared e to the x squared plus e to the x squared, quantity squared with respect to x. And that is the perimeter, right? So again, the blue and red part of the perimeter I could find without using any BC calc. It was actually more geometry and a little bit of algebra, but I had to have an integral for the arc length section, which was the curvy piece of the curve.